All right, so start of Unit 3 here, guys. In Unit 3, we'll be looking at various types of circular motion. Okay, we'll start out with the simplest, which is uniform circular motion. That is something moving in a circle at a constant speed. Okay? Only at a constant speed, though, not at a constant velocity. Any ideas why something can't travel around and around in a circle at a constant velocity? Right. If you're going around in a circle, you're constantly going in a different direction, and velocity is vector. Okay? Therefore, the velocity is always changing. Its magnitude might not be changing, okay, because it is constant speed after all. Okay? So the magnitude isn't changing, but the direction always is. So what that means for us then is there's always a change in velocity. If there's always a change in velocity, what's the object always doing? Accelerating. If something is going to accelerate, there has to be a what? What kind of force? Starts with N. Nope, not normal. Net. Yeah, there has to be a net force. So for something to move in a circle, a net force must be constantly acting on it. And that net force is always directed the same way. Even though the velocity is always changing, the acceleration and the net force always have the same direction. That direction is where? In, towards the center of the circle. All right, think about it. If you whirl something around and around in a circle, I just happen to have this multi-purpose yet virtually budget-free demonstrating device that I used before. Okay, it's like especially cool because it can be used for many things. It's not just a pendulum, it's also something that goes around and around in a circle. Okay, so if it goes around and around in a circle, okay, you think about it, when you're doing that, you're always feeling a pull. Okay, you're feeling a pull out, but you're always pulling in. All right, now if I let it go, I won't. If I let it go, if I were to let it go, what would it do? Okay, it would go, Dom, it would go, right, wherever I let it go from, that's the way it's going to go. Straight line. It doesn't arc. Okay, people get this idea that if something's moving in a circle and I let it go, it's going to like arc outwards. It's not. It's actually going to go in a perfectly straight line out from the point where the force disappeared. Because once the force disappeared, the net force becomes 0. And anything that has a net force of 0 can't change direction. It will travel at a constant velocity after that, according to Newton's first law. All right, so while we won't be doing as much of the like net force calculating, in fact, we won't be doing basically any of that, okay, in this unit, those laws of motion that we learned in dynamics still apply here. Okay, they still govern what an object moving in a circle does. All right, so that covers a few of the key points here. Understand what circular motion is when something moves in a circle. Shocking. Okay, understand how circular motion happens. It happens because something is being pulled towards the center. Okay, that prevents it from going in a straight line. There's a net force. Okay, and understand the relationship between period and centripetal velocity. All right, so this is a new term for us in physics. Okay, period is the time for one cycle. Okay, that's what the term period means, the time for one cycle. Okay, now one cycle in this unit is going to mean one complete orbit of the circle. Okay, or one complete movement in a circle, right? So the time it takes for that to happen is the period. All right, so with uniform circular motion, the motion of an object traveling at a constant or uniform speed along a circular path. But as we can see, if we draw vector arrows, okay, like here and here, for that plane that's attached to a string, the arrow is always pointing a different way, but always has the same length. All right, so its magnitude isn't changing, but the direction always is. Okay, so we can see that something is moving at a constant speed, but not a constant velocity. Right, and that leads us back to this idea that it must be accelerating. All right, if I want to calculate how fast an object is going, okay, since I know it's moving at a constant speed, I would use this formula. Speed is distance over time. But okay with that, right? I can't use velocity here, okay? Because if I talk about one complete circle, what's the displacement of the object? 0, which won't work, right? It'll tell me it has a velocity of 0, which isn't right. So I'm going to find the centripetal speed here, okay, using the distance it travels and the time it takes to do it. But because this is a circle, okay, what do we call the distance around a circle? Okay, so the circumference. How do I calculate that? 2 times pi times radius, right? 2 pi r, or pi times diameter, whichever you have. Usually in physics, it's radius. Okay, so I have 2 pi r, and then the time it takes to go around the circle one time is period. We symbolize that with a capital T, okay, because it's a special time, not just any time. All right, so period is the time it takes to go around the circle one time. So really, this formula, which is on your formula sheet, is really just v equals d over t applied to a circular pattern. All right, so really the big thing we need to know here is that period is the time it takes to make one complete circle. All right, so now there's a similar thing that we sometimes use to period. Okay, instead of telling people how long it takes to go around the circle one time, we might tell them how many times it goes around in a second, which is useful if it's something that's spinning like really fast. Okay, what do we call it if we're talking about how many times it does something in a time interval? Starts with F. How often something happens would be its frequency. Okay, so period and frequency kind of measure similar things. Period measures how long it takes to go around once. Frequency measures how many times in a time interval. So in fact, they are actually the inverse of one another. Okay, period would be seconds per cycle. Okay, it's the time for one cycle, whereas frequency is cycles per second. Right? So they're the inverse of one another, which is where this formula comes from. T equals 1 over F. If they're the inverse of each other, that would be true. T is the inverse of F, 1 over F. Okay? And similarly, F would be 1 over T. Okay? All right, so we do use those, not so much interchangeably because they're not exactly the same thing, but they're talking about the same thing from different points of view. All right, everybody okay with those formulas there? Not difficult formulas, we're going to use them a little bit here, and then just as long as we understand how they work. All right, so we're going to do this first example, right? It's that time of year where probably most of us have had our winter tires put on, okay, because that's the safe thing to do, okay? So we got our winter tires on. When they put tires on rims, okay, if you've got your winter tires on a separate set of rims, they're just obviously throwing them on the truck, okay? But if we're actually putting a new tire onto a rim, there's a process that has to be taken into account, and it's called tire balancing. How many people have heard that? Okay, getting your tires balanced. If you've ever driven in a car that doesn't have balanced tires, okay, you'll be driving along and all of a sudden at a certain speed, the car will start to shake. And once you pass that speed, the shaking goes away again. And then as you continue to increase in speed, it'll come back, okay? It's because the process by which tires are made, pouring liquid rubber into a mold and allowing it to cool, does not always distribute the rubber evenly throughout the mold. So there may be slightly more mass on one side of the tire than the other. Okay? If we don't account for that when we put the tire on the wheel, then we'll get this sensation of there are certain speeds where your car shakes violently and becomes virtually uncontrollable. Okay? It's not a safe condition to have. It's also not good for the rotating parts of your car. The wheel bearings and things like that can wear out. Okay? So we want to have the tires balanced. So what the tire shop will do is they'll put your wheel with the tire on their balancing machine. The balancing machine is spring-loaded. So as the tire spins, the machine will detect any oscillations or vibrations of the tire. The machine's computer can tell it where the tire is heavy, and it'll indicate where on the tire weights, or on the wheel, sorry, weights need to be applied. Right? You can often see these on the inside of a rim. So if we're looking kind of older ones used to be, you could see them on the outside. So if this is the tire and here's the wheel, you would sometimes see this little weight, okay, that was kind of just stuck in there, right? That weight was to balance any unequal distribution of rubber in the wheel. Now what they do is they actually stick them on the inside. They're a little flat square, okay, and they just stick them on the inside of the rim, okay, to balance the tire, because, well, it didn't look nice to have it this way. It's more aesthetically pleasing if you can't see it. Okay, so they put them in there. Anyway, the weights are designed to help distribute the weight of the tire and make sure that your car doesn't vibrate at certain speeds. Okay, so we're going to do a little like centripetal velocity kind of thing here with the tire balancing machine as our context. So we have a wheel of a car that has a radius of 0.29 meters. It's being rotated at 830 revolutions per minute. Okay, did they give me a period or a frequency there? This is a frequency. She didn't even realize I was staring at her while she did that. Anyway, okay, so this is a frequency. They have told me how many revolutions happen per time interval, not the time for one revolution. Okay, if they'd have given me the time for one revolution, all right, that would have been the period. So I've got a frequency, okay, so we'll just have a look at how this will solve. We have a frequency of 830 revolutions per minute, okay, and we have a radius of 0.29 meters. Right? The question wants us to figure out how fast is the tire spinning. Right? Now, we just saw that the formula for this is 2 times pi times r over period. Except the question didn't give me period. So what do? We also said that period is 1 over f. Everyone okay with that? We also said that f is 1 over t. I have two options here. I can do this question in 2 steps, or I can substitute into the formula and do this in 1 step. All right? If frequency is 1 divided by t, is this also saying 2 times pi times r times 1 over t? Is dividing by t the same as multiplying by 1 over t? It is. So could I change this formula to look like this? Okay, I say it's 2 pi r times f. It's the same thing, right? Instead of having seconds on the bottom, I now have seconds on the top because frequency is cycles per second. Okay, everyone all right with that? Okay. Or I could just go 1 over the number I have and get period and then stick it in the formula. Either way will work. I just like shortcuts. Okay. Shortcuts are better. Okay. Anyway, so we're going to solve for this one. I'm going to use this formula here. V equals 2 pi r times f. Okay, so I have 2 times pi times the radius, which was 0.29 meters, times the frequency, which was 830 revolutions per minute. How often do we put velocity in meters per minute? I don't think we've ever done that, have we? I can't think of a time where we've done that. So what should I do with that 830 revolutions per minute? Turn it into revolutions per second, okay, by dividing by 60, okay. Okay, so the tire on that machine spins around almost 14 times in a second. It's pretty quick, okay? All right, so there we've got our frequency. I'm going to multiply that by 0.29 and then again by 2 times pi. Make sure you use your pi button. Typing in 3.14, it won't get it done for us, okay? We need the whole pi number. Okay. All right, so the tire is moving at 25.2 meters per second as it spins around on the machine. Okay, is that reasonably fast? Yeah, about what, 85 kilometers per hour, something like that. All right, everybody kind of follow what we did there? All right, so here's what we did. We just took the, we could have done it this way and calculated the period as well, just gone 1 over 830, and it would have been, here's the time for one revolution, 1.2 times 10 to the minus 3 minutes, which we would have turned into seconds, and then gone 2 pi r over t. We'd get the same answer. It's 25 meters per second, no matter how we do it. Okay. All right. So the big thing here, guys, about uniform circular motion, okay? Uniform means not changing, okay? So it emphasizes that the magnitude of the velocity vector is constant. That is, it's traveling at a constant speed, okay? It is equally significant that the direction is not constant, right? So it's not traveling at a constant velocity, which means that it is always accelerating. Okay? It's always accelerating. Okay? That acceleration we call centripetal acceleration, okay? Now, how many people think I might have said or spelt that wrong? Doesn't sound quite right to your ears when I say centripetal. How many people think it would sound better if I said centrifugal? Okay, centrifugal, centrifugal. Okay, here's the problem with the centrifugal versus centripetal. Okay, centrifugal is how they usually say it, but it's centrifugal. Okay, centrifugal force is not a real thing. There is no force trying to make you leave a circle. Okay? A centrifuge or centrifugal force means center fleeing. Okay? There's no forces that are trying to make anything leave a circle. Okay? There's only forces keeping it in the circle. All right? There's that force that's pulling the object spinning around and around in a circle back towards the center. There's no forces that make it want to leave. But it feels like it wants to leave. Okay? When I'm spinning this around and around in a circle, okay, it feels like it wants to leave. I can feel it pulling outwards all the time, right? What's really pulling outwards? If I let go of this, what does the object do? It flies off in a straight line, right? According to Newton's first law. What's a one-word summary of Newton's first law? Inertia, okay? There's no such thing as centrifugal force. There's only inertia. Okay, the object's inertia wants to travel in a straight line. I prevent that by pulling back. Okay, there is a reactive force, okay, that I feel, right? But it's normal force, tension, it's not centrifugal force. Okay, all I really feel is the inertia of the object. It's not trying to pull out of the circle. Everybody follow me there? Okay, centripetal means center seeking. Okay? Centripetal forces are real. Things wouldn't move in a circle if there weren't centripetal forces pulling them back towards the center. Okay? So centripetal means center seeking, and this is a centripetal acceleration because I'm pulling back towards the center, which means the object is feeling a force towards the center. It's accelerating towards the center. It's always accelerating towards the center. So why doesn't it get closer to the center? It's always accelerating towards the center. Shouldn't it get closer to the center? Not necessarily. Okay, remember, my force is just keeping this thing from doing what nature wants it to do, which is travel in a straight line. If it goes fast enough, there's a balance achieved, okay, between the object wanting to go in a straight line and my pulling it back towards the center. Right? This is how we put things in orbit. Right? We put things in orbit by making them go fast enough that the distance they fall back to Earth is accounted for by the fact that the Earth is round. By the way, the Earth is round. In case there's any flat Earth crazies out there, okay? Because flat Earthers are crazy. Okay, the Earth is round. We know that. We put things in orbit around the Earth. Okay, the Earth is freaking round. Okay, so because the Earth is round and the object is falling towards it, okay, it never gets any closer to it. Because the Earth is round, it curves away from it. So it's constantly falling, but it never gets closer to the Earth. Okay? That's why astronauts on the International Space Station feel weightless. They're not actually weightless. They just feel that way because they're constantly falling. Next time you jump off of a diving board, think about it. While you're falling, do you feel any weight? No, because while you're falling, there's no normal force to give you that feeling of weight. You just fall. Okay? Well, if you're on the International Space Station, you're always falling. Always. Okay? Yeah, some people can't take it. Yeah, it's a really disconcerting feeling, okay, because you're weightless and you feel like you're always falling, but you're not. Okay, we'll go over all the effects of like zero gravity and stuff like that in another part of the unit here. But okay, in order to make something move in a circle, I have to make it accelerate towards the center, but it has to be moving fast enough that it never gets closer to the center, right? Because if I've got this thing moving in a circle, okay, it only moves in a circle if I swing it fast enough. If I let it go slower, okay, it slows down and the radius of that circle gets smaller, okay, and then it doesn't work, okay. So there's kind of a delicate balance that has to be achieved there. Okay, so we can calculate centripetal acceleration by taking the speed of the object squared and dividing it by the radius. All right, when we do that, okay, we're going to get, what are the units for acceleration? Meters per second squared. So if I take v squared, that's going to be meters squared per second squared, and I divide that by meters, okay, the squared meters goes away, and I'm left with meters per second squared. All right, so I can calculate my centripetal acceleration, that is the rate at which the object is attracted to the center, okay, by taking v squared over r. Okay, now, there's lots of real world situations where centripetal acceleration is important. Most of them involve, many of them, involve driving, especially around corners. Okay. If you're just taking a corner in town, what keeps you from sliding out? Friction. Friction can actually act as a centripetal force. Okay. It sticks your tires to the ground and allows your car to traverse a corner. If it's really icy and you try that same trick, you may not succeed because friction will be too small. And as a result, the radius of the circle you are traveling in becomes very large, like essentially it becomes a straight line. And that's disconcerting because you see that car, fire hydrant, tree, house, okay, coming at you, and there's nothing you can do about it because you've done the Canada's Worst Driver thing and slammed on the brakes and gripped the wheel in a death grip while turning it as far to the left as possible and accomplishing absolutely nothing. Okay, you've all done it. We've all done it. Okay, you have to outsmart your own instincts, right? Because our own instincts are, well, if I'm sliding, I should press the brake pedal harder. Okay, we all do it because that's our instinct. Okay, the fact of the matter is I should actually let off the brake. Why should I let off the brake? So my tires will roll. I will have a better chance of traversing the corner with my tires rolling than if they are sliding. Okay, that's that whole static friction versus kinetic friction thing we talked about in the last unit. Okay, it's counterintuitive though. Okay, we want to slow down, we want to stop. We see that car, tree, fire hydrant, house coming towards us. Okay, and we want to make sure we stop, except we actually have to let off the thing that would stop us in order to turn away from that object. Okay, all right, so that all provides a centripetal acceleration. It's also the acceleration you feel if you have a crazy friend and you're riding in the passenger seat with them. Okay, your crazy friend takes corners at too high a rate of speed, and what happens to you? You get thrown around inside the car. Okay, that's why there's a holy crap bar on the passenger side. Okay, that the little thing there on the C-pillar, you just grab onto that. Okay, that's the holy crap bar. Okay, if you drive with a crazy friend, hang on to that thing because it will keep you from smashing your head against the passenger window. Okay, it's even worse. I had a friend in high school who had a Jeep YJ with no doors. Okay, yeah. Yeah, I'd make sure you wear your seatbelt no matter what, but I mean, if you didn't wear your seatbelt in that thing, you would fly out the side, okay, because he drove crazy, right? So yeah, first off, you should never drive in a car with no doors. That's just crazy, okay? There's no reason to drive in a car with no doors. Race car drivers weld their doors shut, okay? So yeah, drive in a car with doors. Otherwise, Newton's first law will cause you to leave the car in a straight line, which is bad. We don't want that. Okay. All right, on that note, in a rollover, are you better to be in the car or out of the car? In the car. You know what kills most people in a rollover? Being crushed by the car. Okay? If you are ejected from the car during a rollover, okay, you will be ejected in such a way that you will fly forward in front of the rolling car. And the car will then roll over you. Okay, that's usually what happens in a rollover. Okay, so if your car is doing this, okay, and rolling like this, you are likely to be ejected at the point where you'd be moving the fastest. You're not going to be ejected down here because you can't be ejected when that part of the car is against the ground. Okay, you are most likely to be ejected at the highest point. Okay, so you'd be thrown in a straight line. There'd be less resistance on you because you're flying through the air. There's more resistance on the car, so it slows down faster, which means you hit the ground in front of it and then it rolls over you. Okay, that's what kills most people ejected from a car in a rollover, is actually being rolled over by the car. That wouldn't happen if they had their seatbelt on and they stayed in the car. The safest place to be in a rollover is in your seat. Okay, remember that. Seatbelts are important. Okay, it's Newton's first law that kills you in an accident of any kind. Stay in the car. Okay, all right. Making sense? All right. Okay, so centripetal acceleration, okay, is the result of, we were saying here, the speed of the object, okay, which is always, or the velocity of the object, which is always tangential to the circle. What does tangential mean? Tangent, what does tangent mean? It touches it but doesn't cross, right? It's perpendicular, okay? A tangent line is always perpendicular to the center. All right, so we have this velocity that's going this way, our acceleration and net force that are directed towards the center, okay? And those two things acting in concert produce this. Effectively, what's happening is that you have an object that's wanting to go in a straight line, but is being pulled towards the center, but wants to go in a straight line, but is being pulled towards the center. And what eventually happens is you start creating an arc that becomes a circle. Okay, that arc becomes a circle. Okay, if I draw that, if I continued to draw that, it would eventually get to the point where I would go all the way around and come back and meet it again. Okay, that's how an orbit is achieved. That's how all circular motion is achieved. Okay, it's a combination of the speed of the object, velocity of the object, and the acceleration back towards the middle. Okay. Now, centripetal acceleration is a vector quantity. Do I need to write, if a question says calculate the centripetal acceleration, do I need to write the vector? Centripetal defines the vector. Centripetal is always directed towards the center. Okay, so unless the question specifically says, give the magnitude and direction, which would be like the simplest answer to have, towards the center, of the centripetal acceleration, okay, you just, centripetal means towards the center. You don't need to indicate that it's towards the center unless the question specifically asks you to do so. Okay. All right. David and Goliath. Example of physics. David killed Goliath with a sling and a stone. Okay? A sling is really just a strap. Okay? It was made out of either leather or hemp, one or the other. Okay? If in David's time, it probably would have been braided out of hemp. That's what they would have had. Okay, so they would have this strap essentially. Okay, and it would have a pocket in the middle. All right. When you use a sling, basically you just whirl something around and around in this pocket. Okay, and then you let go of one end of the sling. Okay, when you let go of it, the force that was holding the rock in the circle is now 0. So what does the rock do? It travels in a straight line from the point of release. All right. Now, that means that just whirling this thing around and around in a circle and then letting it go is the same as what David did to kill Goliath. Now, if I wanted to actually hit a target with this, okay, how accurate do you suppose I could be? Probably not that accurate, but I probably didn't do it every day in defense of all the sheep in my flock either. Okay, wolves don't, come and need me to throw rocks at them every day, right? But if you were David, that was his job. Okay, all day he had to protect the flock of sheep he was responsible for, and the only weapon he would have had to defend it from wolves and bears and things like that would have been his sling. Okay, now you probably think, yeah, but it's a rock. Like, you can't kill something with a rock. Well, you know what? Like, if we threw a rock at somebody, you're right. I mean, it would be pretty hard for us to generate enough speed that we would probably kill somebody by throwing a rock. But by putting it in a sling, what have I just done to the length of my arm? I've extended it, okay? Which now means I can make that rock go faster. Okay, so a sling is like a lever almost. It's a force multiplier. It allows me to make that rock move at a higher rate of speed. Okay, and if I've practiced and I'm accurate, I could very easily break the skull of any animal that happened to get in the way of the rock. Okay, so I'm going to show you. They did a mathematical and physical demonstration of how plausible this is. It wasn't Mythbusters, it was actually the History Channel, okay, that did this, okay, and they proved that unequivocally, yes, it would have been possible for David to have killed a giant using just a sling and a rock. Okay, so I'll show you that video here. Okay, so what that shows us is that obviously once that force is gone, okay, in the case of a sling, once it's called the trigger knot, okay, because he said you have the ring that goes around your finger, and then you have the other end which you keep in a pinch, okay, that's the trigger knot, that's what you let go of in order to release the stone, okay, so he would let go of that, and then it would travel in a straight line because now the tension in the sling is gone. The sling will just flop open, okay, and the rock will travel in a straight line from the point at which he released it. Okay, so that's the important thing there. Okay, remember that centripetal means center seeking. All right, so the effect of radius on centripetal acceleration. Okay, common sense would say if I take this small corner at 28 meters per second and then this corner, which is 3 times larger at the same speed, which one am I going to feel more thrown to the outside in? The first one, yeah, the smaller corner. The tighter the corner, the more I have to change my velocity. Okay, over a wider corner, I don't have to as much because I have more distance over which to make this turn happen. Okay, in a sharp corner, obviously, I'm going to feel that a lot more. All right, which is why we want to take a corner wider. Okay, if it's a little bit icier and we can take it a little wider, okay, that's a good idea because we're going to need less friction to hold us in there. All right, so what we want to do is calculate the centripetal acceleration experienced in both turns. So the formula for centripetal acceleration is A equals V squared over R. Now, just looking at this formula, okay, V is going to be the same in both situations, but one corner is 3 times larger than the other. So looking at this formula, the acceleration for the second corner is going to be how many times smaller? 3 times smaller. It's going to be an inverse relationship here, okay? R is not squared. V is squared, R is not. All right, so if we do this calculation here, we're going to have 28 squared divided by 320. All right, so that's 2.45 meters per second squared. All right, that's a fair amount of acceleration to go around a corner at. Okay, I mean, it's not something a car couldn't handle, but if you were in that car, you would certainly feel pushed towards the outside of the corner, okay, in that situation. And then for this one, okay, we would have 28 squared divided now by 960. All right, so we're looking at 0.816, right? If I multiply that by 3, I get 2.45. So 0.816 meters per second squared, okay, would be a much more comfortable experience for the occupants of the car, and it would be a much safer corner to take if it was icy or anything like that. All right, so the relationship there between R and radius and acceleration is the larger the radius, the smaller the acceleration, and then also the smaller the centripetal force would need to be. Okay, and that's what we're going to be looking at here coming up is centripetal force, okay, more than centripetal acceleration. All right, so that's what we just did there, and we can see that that's the relationship that holds true. Okay. Okay, so in question number 2 here, we already talked about what keeps a car in a corner without skidding. That's going to be friction. Okay, if a ball is tied to the end of a rope and spun in a horizontal circle, what's acting as the centripetal force? The tension in the rope. Okay, what about for the moon moving around the Earth? Gravity. Okay? Gravity acts as a centripetal force. The second half of this unit is going to be basically us looking at, orbits and gravitational relationships and things like that. Okay, so gravity is a very, very common centripetal force. Okay. All right. For question number 5 here, if you're pedaling a bike at a constant rate, describe the motion of the bicycle if the wheels were not circular but oval. Would that be a smooth ride? No, because what's always changing about the wheel? Yeah, it's radius, right? At some points the radius is quite large, which means at those points you're going to go slower. And then when you're dealing with the skinny part of the oval, that part would go faster, okay? Which is why you'd have that sensation of, up, down, up, down. There'd be parts where you go faster, parts where you go slower, because the radius is changing, okay? That's why if you bend a wheel, okay, by hitting, a curb really hard, okay, or you get in an accident and the wheel is bent, you have to replace the wheel. You can't drive on a wheel that's even bent in the slightest, okay? If it is, you'll have that problem. You'll have this oscillation that happens. The car will vibrate, okay? It won't be safe to drive. All right. Number 6, relative speed of a pebble stuck in the tread of a bike tire and the ground. So if I'm riding a bike along the ground, I've got a rock stuck in the tread, okay? The relative speed, okay, as they go past each other. Okay? One's moving kind of forward, the other's moving from that perspective the other way, okay? Now, where are you most likely to have a rock come loose from a tire? It's actually at the bottom. I know, but you'd think it would be at the top, right? But if it came loose at the top, you'd never get one in the windshield because it would throw it into the wheel well, right? It would always throw it kind of forwards on the car, but it always throws it backwards, okay? And this has to do with vertical circular motion, which we'll talk about a little bit later, okay? The issue here is that with a vertical circle, okay, you're moving fastest at the bottom, okay? Now, obviously, when it's a wheel on a car that's moving at the same speed everywhere, but the forces are at their greatest here at the bottom. The most force is required here at the bottom to keep the rock in because gravity wants to pull the rock out. Okay, it wants to pull it downwards. Whereas at the top of the circle, on the top of the tire, gravity is helping to hold the rock in the tread. Okay, but down here, gravity's trying to pull it out. So you've got the inertia of the rock wanting to do this. You've got gravity trying to pull it out. It's most likely to come loose right there and travel in a projectile arc that encounters your windshield. Okay, now, if you're just driving behind somebody on the road, you're just on the highway, you're both traveling at a constant speed, is that likely to happen? When is it more likely to happen? Traveling at a constant speed or accelerating? Yeah, okay. There's a certain speed at which those forces will add up to a point where the rock is going to come loose. Okay, if you're traveling behind someone at a constant speed and the rock hasn't come out, it's probably not going to, unless they accelerate and produce more inertia for that rock to want to leave. Okay, so it's usually when a car is accelerating that it's going to throw the rock. Okay, it's not usually when it's traveling at a constant velocity that the rock will come out. So keep that in mind. You don't want to get rocks in the windshield. Don't follow an accelerating car too closely. Okay, that's when it's most likely to lose a rock. Okay. Questions on centripetal acceleration, uniform circular motion? All right, I'm going to give you about a 5-minute break here while I get centripetal force ready here. Okay.